Hi, my name is Harsh, and today I will talk about randomized treaps. First, I would like to talk about treaps. Treaps are binary tree data structures that store pairs of values, which are of the form ki, pi, where ki are the keys and pi are the priority values. These priority values need to be distinct. The binary tree, which is the treap, is arranged in the form of a binary search tree with respect to the keys, and it is arranged in the form of a min heap with respect to priority values. What that means is that the tree follows the heap order property with respect to the priority values. I want to prove a very important result for trees. It is that given a set of pairs k1, p1, k2, p2, all the way up to kn, pn, there's only one arrangement of a tree, no matter in which order these pairs are inserted and no matter how they are inserted. The proof is by induction on the number of nodes. The base case is obvious. The base case is n equals 1, so there's only one pair. When there's only one pair, there's only one node, and thus only one arrangement. For the inductive hypothesis, we assume that the statement is true for all values of n less than k, and for the inductive step, we prove it for n equals k. So, when n equals k, we select the pair with the lowest priority value as the root. This pair has to be the root because the heap order property needs to be satisfied. Thus, the root needs to have the least priority value. Now, all the nodes of the left subtree are nodes with a key value which is lower than the key value of the root, and all the nodes of the right subtree are those pairs which have a key value which is greater than the key value of the root. Now, since the left subtree and the right subtree need to be trees by themselves, and since they have less than k nodes, they are unique by the inductive hypothesis. Since the root is unique, and the left subtree is unique, and the right subtree is unique, the whole arrangement needs to be, unique. Thus, the statement is proved. Now, I would like to talk about binary search trees. Binary search trees are basically data structures that were formed to optimize insertion, deletion, and search times. Now, if binary search trees are implemented in a trivial manner, that is, if no balancing is done, if no rotations are done, they tend to be very inefficient for certain inputs. For example, if the keys are inserted in the order of 1, 2, 3, 4, all the way up to n, you find the tree that I've drawn on the left. In this case, the average search time is big O of n, the average search time among all values. The average insertion time is big O of n. The average deletion time is big O of n. Now, this is similar to array search or array deletion. The time taken for search and deletion in this tree is similar to array search or array deletion, which is big O of n. And in the case of insertion, it is even worse because in the array you can simply push to the end of the array. But practically, it is even worse than array search or array deletion. That is because the arrays are copied from memory into cache, and they are copied in complete chunks, so the processing is faster. But the nodes of the trees need not be located close to each other, thus multiple copies may be required. Therefore, in reality, trees, trivial binary search trees can be worse than arrays. Some deterministic solutions were created to solve this problem. The solutions include data structures like spray trees, AVL trees, and redback trees. These are basically self-balancing binary search trees. In order to balance the binary search tree, they rely on tree rotations. The asymptotic time complexity of a single tree rotation is big O of 1. I've drawn an example of a tree rotation below. There's two types of tree rotations, right rotate and left rotate. I've drawn an example of right rotate. If you perform right rotate about node A on the first tree, you get the second tree. And if you perform left rotate on the second tree about B, you get the first tree. So this is how rotations work, and this is what is used by many data structures to balance the binary search trees. These deterministic solutions have some disadvantages. The first major disadvantage is that these data structures have a very complex implementation, especially in the case of red-black trees. In the case of red-black trees, for example, you have to check what the color of the parent is, what the color of the children are, how they match, and based on these conditions, you have to make many complex decisions on whether to rotate or whether not to rotate, which direction to rotate in, and so on. The second major disadvantage is that they rely on too many rotations. especially in the case of split trees. So split trees basically have an amortized time complexity of big of log n, and this analysis requires us to have many rotations. Now, rotations do have an asymptotic time complexity of big of 1, granted, but practically they tend to be very slow because the constant is very high. In order to perform a particular rotation, processors need to read and write multiple times. This tends to be expensive and is much worse than simply reading once. So therefore, these deterministic solutions have some disadvantages that need to be solved. This is where randomized treaps come in. Randomized treaps are basically another implementation of a self-balancing binary search tree. They have an expected height of big O of log n. Thus, the expected search time, the expected insertion time, and the expected deletion time is big O of log n. And the expected number of rotations per insertion or deletion is less than 2. So that is also optimal. There's not too many rotations. Now, I would like to talk about the insertion algorithm for randomized treaps. In order to insert a particular key into a randomized treap, the following steps need to be followed. If you may recall, in treaps, keys are also associated with a priority value, and these priority values are distinct. We need to pick a unique priority value for the key to be inserted. This unique priority value can be chosen from a uniform distribution between 0 and 1. The implementation of the uniform distribution is not important to us, so we just think of it as a black box. Once we have selected a priority value for this key, we perform a normal BST insert for this key value pair. We only look at the key value for now. Once the BST insert is done, the new key is added as a node, as a leaf node in the binary search tree. What we need to do now is balance this randomized tree. We balance the randomized tree by making sure that the heap order property is not violated and that the heap order property is maintained. What we do is that we compare the priority value of the newly inserted node with the priority value of its parent. If the priority value of the newly inserted node is less than the priority value of its parent, we need to perform a rotation about the parent to bring the newly inserted node up. Now, how do we make a decision between which rotation to make? Well, if the newly inserted node is the left child, we perform a right rotation. If the newly inserted node is the right child, we perform a left rotation. We continue this process on the newly inserted node until we get to a point that the newly inserted node is in a situation that its priority value is greater than the priority value of its parent. So that is how insertion is performed in randomized treaps. Now I would like to talk about the deletion algorithm for randomized treaps. In the deletion algorithm, we are given a key and we are supposed to delete that key from the randomized treap. First of all, obviously we need to search for the node containing the key. We do this by performing a normal binary search tree search, a BST search. Once we have found that node, we need to delete that node. In order to delete a node, what we do is that we look at its children. If either of its children is null, we delete the node and we replace it by its other child. Now, the other child can of course be null, but that's besides the point. If neither of its children are null, we need to perform some rotations to bring the node down. So what we do is that we compare the priority value of its two children. If its left child has a lower priority value than its right child, we perform a right rotate. Otherwise, we perform a left rotate. We keep doing this until we get to a point that the node to be deleted has at least one child that is null. Once we get to that point, we replace the node with its other child, and then we have deleted the node. Now, I would like to prove that the expected height of a randomized treap given any set of keys as input is big O of log n. This proof is very interesting and it is similar to the proof of a randomized binary search tree's expected height. The proof goes as follows. We first establish that given any set of pairs of keys along with the priorities, the order of insertion doesn't really matter and it doesn't really affect the height of a randomized treap. If you may recall, given any set of pairs of keys along with their priorities, there's only one arrangement of treap that can be formed. So the insertion order doesn't really matter, right? That is why this statement is true. The second thing that I would like to establish is that it doesn't matter when we are assigning priorities. So, what we are doing is during insertion, we are first assigning a priority to a key, and then we are inserting into the tree, and then we are balancing. However, if the priority was already available with the key, there would no difference would be made. Like if the same priority was already available with the key, for example. So these are two facts that I would like to establish first. So analyzing the expected height of a randomized tree given a set of keys that is created in the way that we have created it by multiple insertions is analogous to having the keys in the beginning and assigning a randomized priority to each of the keys and then inserting them in any order, right? So it is analogous to having a set of keys along with the priorities in the beginning and finding the expected height for the trees that would be formed given the set of keys along with the priorities. So what really matters is the relative order of the priorities of these keys and which key has the lowest priority among all of these keys. This key priority pair will always be the root. In order to proceed this proof further, we first create a random variable called Rn. Rn is the rank of the root's key given n nodes. The root is obviously the key with the lowest priority value, with the least priority value. Rn is its rank in a sorted array of keys. So if the key is the fifth smallest key, the value of Rn is 5. Rn can be any of 1, 2, 3 all the way up to n with equal probability, since the priorities are assigned independently at random. So any of the nodes can have the least priority. We create another random variable xn, and xn is basically what we are concerned with, what we are dealing with. We need to calculate the expectation of xn. Xn is the height of a randomized tree given n nodes. We create another random variable called yn, which is essentially 2 raised to xn. So increasing xn by 1 results in yn doubling. The proof is essentially along the lines of we first prove that yn is polynomial in n, and as a result, xn would be logarithmic in n. Next, we create n new random variables, z and I, for all values of I from 1 to n. Z and I are indicator random variables, which indicate whether Rn is equal to I. So basically, Z and I is 1 if the ith key is the root, and 0 otherwise. Trivially, the expectation of Z and I is 1 by n, since either of the keys can be the root with equal probability. Of course, I symbolizes the rank of the key. So if Rn equals I, the left subtree of the root would have I minus 1 nodes, and they would have ranks from 1 to I minus 1. The right subtree would have n minus I nodes, and they would have ranks from I plus 1 to n. So xn is equal to the maximum of the heights of the left subtree and the right subtree plus 1, because there's also the root. And consequently, yn is going to be 2 times the max of yi minus 1 and yn minus I, since increasing xn by 1 doubles y. Now, of course, this expression is that we are given Rn equals I, but if we are not given what the value of Rn is, xn can be written as follows. It is 1 plus summation of I equals 1 to n, z and I, max of xi minus 1, xn minus I, because z and I are basically indicator random variables indicating which of the I keys are the root. For the rest of them, z and I is going to be 0, and for the root, z and I is going to be 1. Consequently, yn can be written as summation of I equals 1 to n, z and I 2 times max of yi minus 1, yn minus I, because in this case, we don't need to know the root beforehand. We take expectation on both sides, and because of linearity of expectation, we can take the expectation inside the summation. Now, of course, z and I and yi are independent because yi basically is the height of a tree given n keys and priorities. It doesn't really depend on any external factors. It only depends on the relative order of the keys that we are given. And z and I is also not dependent on yi because it is obviously the key with the lowest priority value. It doesn't depend on the height of the subtrees. Therefore, we can split the expression using this independence. Once we have split the expectation, we can write expectation of z and I as 1 by n. We worked that out in the previous slide. And then we can say that the maximum of yi minus 1, yn minus I is less than the summation of yi minus 1 and yn minus I. That is obvious. And we can spread this using linearity of expectations. Once we have split this, we can simply split the summation too. We can split the summation into summation of expectation of yi minus 1 plus the summation of expectation of yn minus I. Both are equal. Both are basically the symmetric opposites of each other. So we can simply write that as 2 times the summation of yi minus 1 And we can write that as 2 times the summation of expectation of yi from I being 0 to n minus 1. After this, we apply guess and substitute. We claim that expectation of yi is less than or equal to 1 by 4 times I plus 3 choose 3. And we prove this is true. So expectation of yn consequently would be less than 4 by n times summation of I equals 0 to n minus 1 based on the previous expression. Expectation of yi, which is less than or equal to, based on the guess and substitute, the value that we've guessed, 4 by n times summation of I equals 0 to n minus 1, 1 by 4 times I plus 3 choose 3. It consequently, the 4 and 4 cancel out, and the summation of I equals 0 to n minus 1 using some identity, it comes out to be n plus 3 choose 4. Once that is done, we can expand the expression to n plus 3 factorial by 4 factorial times n minus 1 factorial. N and n minus 1 factorial can get multiplied together to form n factorial, and out of 4 factorial, we remove 4, and we write that as 4 times 3 factorial. So this n plus 3 factorial by 3 factorial times n factorial can be written as n plus 3 choose 3. And this proves that expectation of yn is less than 1 by 4 times n plus 3 choose 3. So the guess and substitute is proved. So expectation of yn, as we can see, is a polynomial here. So n plus 3 choose 3 is like a 3-degree polynomial. Since yn is a polynomial, expectation of yn is a polynomial, expectation of xn is logarithmic in n, right? Because, the log of n cubed is still 3 log n. Therefore, we prove that the expected height of a randomized treep is big O of log n. Next, we need to prove that the expected number of rotations during insertion or deletion is less than 2. We prove this for insertion for the time being, but it's similar for deletion. So we prove this by proving a couple of statements first. So first, let me make some definitions. First, the first definition is of C. So C is the length of the right spine of the left subtree of a node X that has been inserted, that has just been inserted. So after X has been inserted, the length of the left spine, of the right spine of the left subtree is C. And similarly, the length of the left spine of the right subtree is D. We use these definitions to prove the next statement. The statement is that the number of rotations used during the insert of the node X is equal to C plus D. So once the node X was inserted as a leaf, C plus D rotations were used to get it to the current position. Of course, the definitions of C and D are as in the previous slide. The proof is inductive. We perform induction on the number of rotations. The base case is quite obvious. The base case is that the number of rotations, which is k, is equal to 1. So when k equals 1, the new node was inserted as a leaf, and only one rotation was used to get it to its current position. You can see in the diagram that this is the case for right rotate. The same case can be made for left rotate. Once right rotate is performed, the parent of X becomes its right child, and the right child of A, which is the parent of X, is still the right child of A. So A doesn't have any left child anymore because X didn't have any right child. Because if X had a right child, that would be the left child of A. But since X is a newly inserted node, it doesn't have any right child. So the length of the left spine of its right subtree, of the right subtree of X, is equal to 1 because it only contains A. And the length of the right spine of the left subtree is equal to 0 because it doesn't have a left subtree. So C is equal to 0 and D is equal to 1 and C plus D is equal to 1. Therefore, C plus D is equal to the number of rotations. Therefore, the statement is true for the base case of k equals 1. Next, we claim an inductive hypothesis. The hypothesis is that the statement is true for all values of k less than t. K is, of course, the number of rotations. Next is the inductive step. We need to prove the statement for k equals t. So in order to perform t rotations to get it into its current position, first t minus 1 rotations are performed, right? So, first t minus 1 rotations are performed to bring it into a position that is just below its required position, and then one more rotation is performed. Now, after performing t minus 1 rotations, what happens is that it reaches a particular position and it has a left subtree with right spine length 3 prime and it has a right subtree with left spine length d prime. Now, according to the inductive hypothesis, C prime plus D prime is equal to the number of rotations, which is T minus 1. So C prime plus D prime is equal to T minus 1. Without loss of generality, let's assume we perform right rotate. Okay, the same case can be made for left rotate. When we perform right rotate, as you can see in the diagram, its left subtree remains its left subtree. So the left subtree length is C prime. So C is equal to C prime. And its right subtree consists of its previous parent A, and the children of A are the previous right subtree of X and the previous right subtree of A. Now you can see that the length of the left spine of the right subtree is equal to D prime plus 1 because D prime comes from A3, which used to be the right subtree of X, and the 1 comes from A. So D is equal to D prime plus 1. And C is equal to C prime, as we've talked about before. Now, C plus D is equal to C prime plus D prime plus 1. By inductive hypothesis, we have stated that C prime plus D prime is equal to T minus 1. So C plus D is equal to T minus 1 plus 1, which is equal to T. And that is equal to the number of rotations required to bring X to its current position. So the inductive step has proved the statement. So because of the previous result, in order to calculate the expected number of rotations during insertion, we need to only calculate the expected value of C and D, and the expected number of rotations is equal to C plus D. Without loss of generality, we can assume that the keys are 1, 2, 3, 4, all the way up to n. And the reason for that is only the relative order of the keys matters. It doesn't matter what the actual values of the keys are. So for example, if one key is 3 and the other key is 5, or one key is 2 and the other key is 3, only the relative order matters, and that is because we are performing comparisons during insertion to insert something. We are never really using the values of the keys. So the proof goes as follows. For nodes x and y, we set k to be equal to x dot key and I to be equal to y dot key. So we select two nodes x and y, k is equal to x dot key and I is equal to y dot key. Next, we create a set of random variables which are of the form xik. This is an indicator random variable which is 1 if y is in the right spine of the left subtree of x. So if you remember, the length of the right spine of the left subtree was c, and if y is on that right spine, then xik is 1. Otherwise, xik is 0. K is again the key of x, and I is the key of y. Next, we show that xik can only be 1 if these three conditions are satisfied. The first condition is that the priority of y has to be greater than the priority of x. Second, the key of y has to be less than the key of x. And third, for every z, such that y dot key is less than z dot key is less than x dot key, which means that z is between y and x, the priority of z has to be greater than the priority of y. First, we prove the if statement, which means that if the three conditions are true, xik has to be 1. The second condition, which is y dot key is less than x dot key, basically eliminates the possibility of y being in the right subtree of x. So y cannot be in the right subtree of x, because if it was in the right subtree of x, y dot key would be greater than x dot key, which violates the second condition. Now, y can be in two positions. It can either be in the left subtree of x, or it can be in a completely different subtree altogether. Let's assume that it is in a completely different subtree altogether. If y is in a completely different subtree altogether, y and x must have a common ancestor, z. Let's assume that z is the lowest common ancestor of y. Now, since z is the lowest common ancestor of y, the value of z must lie between y and x. So the value of z is less than the value of x, and it is greater than the value of y. But since z is an ancestor of x and y, the priority of z is lower than the priorities of x and y. This violates the third condition. The third condition states that if for every z such that its key lies between the keys of x and y, its priority has to be greater than the priority of y. However, its priority is less than the priority of y. So this violates the third condition. Therefore, y cannot be in a completely different subtree altogether. It has to be in the left subtree of x. So the only position for y is in the left subtree of x. Now, we have proved that y is in the left subtree of x. We need to prove that y is on the right spine of this left subtree. We do this as follows. First, we assume that y is not in the right spine of the left subtree. This can only be possible if y is in the left subtree of any node that is in the left subtree of X. So there has to be like from the path from the left child of X to Y, there has to be at least one left turn. Um, let's say that the node from which we took the first left turn is Z. Okay, so the key of Z would have to be greater than the key of Y. The reason for that is that Y is in the left subtree of Z, so the key of Z would have to be greater than the key of Y, and the key of Z is less than the key of X, and that is because Z is in the left subtree of X. Now, the priority of Z is less than the priority of Y. That is because Z lies above Y and Z is an ancestor of Y. This violates the third condition again. It cannot be the case that Y is not on the right spine. Y has to be on the right spine of the left subtree of X. Next, we prove the only if condition. We prove that if xik equals 1, the three conditions are true. The conditions 1 and 2 and 3 are true. The conditions 1 and 2 are obviously true because if xik is equal to 1, it means that x is an ancestor of y, and that means that the priority of x has to be less than the priority of y. And the second condition is true because if y is in the right spine of the left subtree, it is in the left subtree of x, then the key of y has to be less than the key of x. Now, in order to prove the third condition, we assume that there exists some z such that its key lies between y and x. However, its priority is less than the priority of y. So we consider some possibilities. The first possibility is that z lies in the right subtree of x. This is not possible because the key of z is less than the key of x, so it cannot lie in the right subtree of x. The second possibility is that z lies in the left subtree of x. If this is the case, z can only lie in the right subtree of y. This is because since y lies on the right spine of the left subtree, the only values that are greater than y in the right spine are the keys that are in the right subtree of y. So z has to lie in the right subtree of y. However, if this is the case, then the priority of z would have to be greater than the priority of y. But we assumed that the priority of z is less than the priority of y. Therefore, this leads to a contradiction. Now, we need to consider a third case. The third case is that z lies in a completely different subtree altogether. If z lies in a completely different subtree altogether, then z and x must have a lowest common ancestor z prime. Z such that x lies in the right subtree of z prime and z lies in the left subtree of z prime. Now, if x lies in the right subtree of z prime, y must also lie in the right subtree of z prime, since y is in the left subtree of x. Since y lies in the right subtree of z prime, the value of y is greater than the value of z prime. And the value of z is less than the value of z prime, since z lies in the left subtree of z prime. So we get the inequality that z is less than y. But this contradicts our assumption that the key of z is greater than the key of y. Therefore, the third condition is proved, since we couldn't find any contradicting case. Once we have proved the statement, we use the statement to find the expected length of C. In order to do this, we first calculate the probability of xik being 1. It is obviously 0 if I is greater than k, because if I is greater than k, then y cannot lie in the left subtree of x. Therefore, it cannot lie in the right spine of the left subtree, since it is not even in the left subtree. From I to k, there are k minus I plus 1 key values. Therefore, there are k minus I plus 1 factorial permutations of the relative order of priorities to be given to keys from I to k that occur with equal probability. Look, the actual values of the permutations don't really matter. What matters is the order of these values, since they are only being compared. So there are k minus I plus 1 factorials in which these orders occur, and they all occur with equal probability. Now, according to the third condition, for every node such that its key lies between the key of y and the key of x, its priority has to be greater than the priority of y. Another thing is that the priority of y is greater than the priority of x, since x is an ancestor of y. If you look at keys from I to k, k is associated with the node x, therefore it must have the lowest priority. I is associated with the node y, therefore it must have the second lowest priority, followed by all the other key values. So we are fixing the lowest priority key. We are fixing the second lowest priority key. Therefore, the number of permutations in this case is k minus I minus 1 factorial. Therefore, the probability of xik being 1 is equal to k minus I minus 1 factorial by k minus I plus 1 factorial. This is as low as 1 by k minus I times k minus I plus 1. Next, we calculate the expected value of c, which is the length of the right spine of the left subtree of x. Now, this is equal to, by the way, x has the key k. This is equal to the summation of probability of xik being 1 for all values of I. Now, of course, if the value of I is greater than k, then probability of xik being 1 is equal to 0. Therefore, we only calculate the probability for values of I being less than k. This is equal to the summation you can see, which is 1 by k minus I times k minus I plus 1. You can transform this into a telescopic series and it comes out to be 1 minus 1 by k. Now, we also need to calculate the expected length of d, since the expected number of rotations is equal to c plus d. We can do this by symmetry. We don't need to go through the lengthy calculations again. We can see that k minus 1 is the number of keys that are less than k, and expectation of c is equal to 1 minus 1 by the number of keys less than k plus 1. By symmetry, d would have to do with the number of keys that are greater than k, and the number of keys that are greater than k is equal to n minus k. So similarly, the expectation of d is equal to 1 minus 1 by n minus k plus 1. Therefore, the expectation of c plus d is equal to the expectation of c plus the expectation of d by linearity of expectations, which is equal to 2 minus 1 by k minus 1 by n minus k plus 1, which is always less than 2 regardless of the value of k. Since the number of rotations required during insertion is equal to c plus d, the expected number of rotations is also less than 2. So the expected number of rotations is also very low, therefore a treep is very optimal. A similar case can also be made for deletion, but the overall point is that randomized treeps require very few rotations. This brings me to the end of the lecture. Thank you.